Okay, this is the PowerPoint that I would have gone through with you in class. I've not done this before, so we'll see how we get on with it. The last bit of this unit that we need to do is we need to go through this bit about spectra. Now, hopefully you've looked through the stuff from National 5 that I sent you earlier in the week, and hopefully that makes sense and has reminded you of what the emission spectra and absorption spectra look like. We just need to go into a little bit more detail about why these lines are produced and how they're produced and what that means. So an emission spectra is the range of colours that you get given out by a light source, and two different types: continuous spectra, which is what you get from white light, and line spectra if it's from a specific element or specific type of light. And we use a spectroscope to look at them, which obviously we can't do at the moment. So with a continuous spectra, so like I say, this is from white light. So if you put white light through a prism, then you get all of the colours on your screen. So that's a continuous spectrum, okay? A line spectra is then where you are just seeing specific colours. So helium lamp, for example, if that helium lamp has got enough energy to be emitting light and you put that through a prism, it only emits light of certain colours. And that's to do with the frequency of the light that is being emitted. And that's what we're going to look at now. To understand why this is the case, we need to look at the model of the atom. So again, this is a bit where those of you who do chemistry are going to have a bit of an advantage over everybody else. So at the start of the 20th century, a guy called, I think his name was Niels Bohr, proposed this model of the atom. And he basically proposed that the electrons are then in specific energy levels. So that it's not just that they're floating about around the outside, like what they originally thought, but that they're in energy levels, or shells, so I think you call them in chemistry. If you don't do chemistry, don't worry about it. Hopefully that little diagram is familiar enough. So basically the electrons are arranged in different shells. You get so many in each one. But they can actually move between them, and that's all you really need to know. What the Bohr model tells us basically is that electrons can only exist in specific orbits, so they can't be in between shells. They'll start from the inside basically and work so closer to the nucleus and work their way up from there. The ones in different orbits have got different amounts of energy, and they can jump between particular levels if they've got enough energy to do so. So basically when they absorb energy, they can move up to a higher level, and then if they then emit that energy, they'll drop back down again. So as they drop back down to another level, they give out energy as they do so, and that energy that they give out is emitted as light, and it'll be at a specific frequency. So this is kind of what it looks like. So the circular diagram isn't necessarily as clear for annotating, so they're drawn then just as lines. In your notes, the printing's gone a little bit weird, and there's a diagram similar to this one, but it's got numbers of specific amounts of energy on it as well. But it's not quite lined up properly. But you should still be able to see it. So the way this is drawn is that first energy level is what's called ground state. So if an electron is the electrons that are closest to the nucleus, so that's the level with the lowest amount of energy, that's the ground level, and that would normally be written as E0. And then the ones from that, after that, they're what are called in an excited state. So you've then got energy levels 1, 2, whatever, depending on how many electrons there are beyond that. If then the electrons are given enough energy that they leave the atom completely, then that's the ionization level. So if they leave the atom completely, then the atom is ionized. So that would be the ionization level. So the one that's shown in the picture is carbon. Carbon's got 6 electrons. 2 of them are in the ground state. 4 of them are in energy level 1. Okay. If they're given enough energy, they can move between the levels. But that does actually just happen kind of randomly. It's a bit like nuclear decay. They will move between the levels. Oops. So the electrons can exist as we just said, in any of those levels. The further away from the nucleus it is, the more energy the electron's got. And one that's gained just enough energy to leave at that point has got 0 joules of kinetic energy. That's the ionization level. What that then means is that when you're looking at how much energy they have got in the energy levels, they've actually got negative energy associated with them. Don't worry about that too much. It doesn't affect your calculations or anything. It's just because the point at which they leave the atom has been set at 0. And so once they've left the atom, they've got positive amounts of energy. So when they're inside the atom, then that's kind of marked as negative. And you'll see that in a minute on another diagram. So most straightforward, the simplest atom obviously is hydrogen, 1 proton. If that's given enough energy, electron will leave, and then therefore it's ionized, like we've just said. So this is showing the energy levels within a hydrogen atom. I'm not quite sure why it's calling it W0 and W1, 2, 3 and 4 rather than E, but never mind. Sometimes if you've got more than one atom, there's a question in a bit that you'll do where one's called X and one's called Y. So yeah, for whatever reason they've called it W in this question. What that's basically telling us is that the one electron in the hydrogen atom is sitting in the ground state. It's in that shell or that level closest to the nucleus, and at that point you would say that it's got minus 21.76 times 10 to the minus 19 joules. That basically means that it needs to gain 21.76 times 10 to the minus 19 joules for it to get to the ionization level to then be able to leave the atom. It can move between them if it's got enough energy. So if it's given approximately 16 times 10 to the minus 19 joules of energy, it'll go from W0 to W1. If you give it another 3 times 10 to the minus 19, it'll go up to W2, and so on. When it then drops back down again, it then gives out these photons of light as it goes down. So, for example, if we say the electron absorbs some energy and it moves from W0 to W2, if you wanted to know how much energy it had absorbed to do that, you would just work out the difference between those two numbers. So roughly 19.3 times 10 to the minus 19 joules, the difference between W0 and W2. When it comes back down again, there's a couple of different options about what it can do. It can drop all the way back down to the ground state in one go. And if it did that, it would release a photon with an energy of approximately 19 times 10 to the minus 19 joules. Or it could drop from W2 to W1, or it could drop from W1 and then it would drop from W1 to W0. So there are 3 different things that can happen as the electron goes back down. It can go all the way back to ground state in one go, or it can step down individually. That means that then there are 3 different pockets of energy released from the atom as it does so. And those 3 little pockets of energy are all at a specific frequency. The more electrons that there are that make a transition between different energy levels, the brighter the line in the spectrum will be. So obviously for hydrogen, you've got less electrons there to be making that transition. But you might have more than one hydrogen atom, so there might be lots of atoms there all doing the same thing at the same time. So if each emitted photon of light, so as they're dropping down, they're emitting this photon of light. And as they're doing that photon of light's got a particular amount of energy. If it's got a certain amount of energy, it means it's also got a specific frequency. And we can work that out using the Planck equation that we did when we did the photoelectric effect. So E equals HF, where E is the energy in joules, H is Planck's constant, which is 6.63 times 10 to the minus 34 joules per second, I think. And frequency is obviously in hertz. So for example, here's one that I've just done for you rather than being able to do it on the board. Just done it on a bit of paper and stuck it in here. So the question is, what colour is emitted if an electron in hydrogen makes a transition from W3 to W1? So all I've done is, going back to this one, is I've noted down the energy required for each level. So at W1 and W3, which I've then written down there. Now, when you're working out because you're just working out the difference between the amounts of energy to get from one to the other, you can forget about the negative. Although I see I've actually written the negative in there, but you don't need to worry about that. So the difference between those two levels in terms of energy is 4.06 times 10 to the minus 19 joules. So we're then just going to stick that into the E equals HF formula. So F then is E over H. Work that out, and we end up with 6.124 times 10 to the 14 hertz. That's a frequency. The question is asking us what colour of light's emitted. So the colours of light are related, obviously, well, they are related to the frequency, but they're obviously related to the wavelength, and that's how we know them. So we then have to do V equals F lambda, so rearrange that, and then speed of light divided by the frequency that we've just got. That gives us 4.899 times 10 to the minus 7 metres, which is 490 nanometers, which is blue light. Okay. So it's fairly straightforward, as long as you're paying attention to what levels you're looking at in terms of where the electron is and where it starts off at and where it ends up at. Okay. So how does this fit into the spectra then? So what that means is it's giving out light at that specific wavelength. Now this is actually going on to look at absorption spectra, and I'll come back to emission spectra in a minute. So if we go back to the fact that all frequencies are present if we've got a continuous spectrum, so the white light. If you then think about the sun, the light from the sun, so the light from the sun is white, but if you were to look through a spectroscope at the light that's coming from the sun, what you would see is more like the diagram at the bottom. It's got black lines across it. So why has it got black lines across it? So basically what's happening there is that the atmosphere of the sun actually contains a lot of sodium. So sodium emits light at those frequencies where those black lines are. So the emission spectrum of sodium would look the same as that bottom diagram, but the other way around. It would be black with red lines and then orange lines and yellow lines at the same places as where those black lines are. If you put white light through a gas that's got a particular emission spectra, that gas absorbs the light at the same wavelengths or the same frequencies as what it emits. So as the light from the sun is passing through the sodium is absorbing the light at particular frequencies. So that means that then what we see is all of the light minus those frequencies. So that's where you get the black lines. Okay? So an absorption spectra is when you've got a continuous spectra that has absorbed light from a particular element. And an emission spectra is the spectra that element will be given out. But the emission spectra looks the other way around. So if I go way back up, so there doesn't seem to be an easy way to scroll through this. So there's your emission spectra. So emission spectra is black with that's actually shown the other way around as well. We've got red on the right rather than on the left, but that doesn't matter. So the emission spectra is black and it's just showing the light that it's emitting, whereas then the absorption spectra is the opposite way around, where you've got the bright colours and it's too far. And it's absorbing the light at those particular frequencies. Okay. So what causes these lines? That's pretty much what we've just gone through. So the light from the sun's passing through a gas, and the gas absorbs any photons that have the same frequency as the photons emitted in its own emission spectra. So as I said, the sodium in the sun's atmosphere is absorbing the light at those frequencies where the black lines are. I keep pointing to the screen, forgetting that you can't actually see what I'm doing. Okay. So that's just explaining about the sodium again. And then again, that's just showing it there. So this sodium, that's obviously just part of it, where the sodium's been absorbed, or the light has been absorbed by the sodium in the atmosphere. So each element has got a different atomic structure. And because each element's got a different atomic structure, that basically means that the electrons in that element are all arranged differently on the different energy levels. So whether they're on the ground state, the first energy level, the second energy level, excited level, third excited level, and so on. They're all in different places because they've all got different numbers of elements. Then they've all then got their own patterns and their own different options about how those elements can move, those electrons can move. So like we said with the hydrogen, that each time, if the hydrogen electron is jumping from ground state to the second excited level, and then it's going to come back down again, it can either drop all the way back down again or just part way at a time. So if you think about if you've got more electrons, that gives you even more options about how many different options there are for when the electrons drop back down through their energy states. And as they're dropping back down and they're emitting light, every time they emit light, that provides a line, or emit a photon, that provides a line on the emission spectrum. So the emission spectrum, the number of lines that are shown on it, will depend on what element it is, and the bigger the element is, the more lines there's going to be. Now this one here, so this is what the black lines from the sun look like. So when we were talking about sodium a minute ago, obviously that's just the bits that are being absorbed from that particular bit of the atmosphere. But if you look at the emission spectra of the sun, what you see is lots of different lines in lots of different places. And those lines are all and that's obviously quite a complex model, quite a complex diagram of it. Those lines are all at different places, they're all at different frequencies, therefore they're all different wavelengths. That then helps to determine what elements are in the sun. Also, the one at the top that shows it with the peak on the graph there, that's where most of the energy is. So the brighter the line, the more photons are being given off at that point. Obviously, that's just a black and white version of it. Astronomers then use the same technique to work out the chemical composition of gas clouds between Earth and distant stars, and between stars and all sorts of things. And that was what was in the PowerPoint that I asked you to look at on Monday, that talked a bit about that, about how you can use basically each element has a fingerprint. So the emission spectrum that each element gives out is like its fingerprint. Okay, what I've done is I have just taken a photo of your notes, and there's pages 18 and 19 as well. I didn't bother taking a photo of those ones, but 20 and 21, I just took a photo of them and I added it in just so that I could just go through whether there's anything else that you needed to know in there. So one bit that's worth pointing out is the bit where it talks about atom X. So first of all, actually, this is just emission line spectra, and then the next page is the absorption line bits. The bit before it in the notes is the model of the atom, and then a kind of recap bit about how the emission and absorption spectra are produced. So the emission lines, how they're created. So I think most of what's on here is what I've already gone through, that at any time an electron in a higher energy level can make a transition to a less excited energy level. So it can move at any point, and that's just a random process. When it does that, it's going to emit some energy, and that energy that is emitted will be the same amount as the difference between the energy levels, depending on where it is it's jumping. The gaps between the energy levels aren't all the same either. So you should see that from that diagram at the bottom, halfway down, where it talks about atom X. So atom X has got 4 possible energy levels. We've got that shown there, and you can see that the difference between energy level 0 and 1 is about 8 times 10 to the minus 19. And then it's only less, about 2.5, and then 1.5. So the difference between each of the energy levels varies. It tends to get, they tend to get closer and closer together as you get further up. So it takes a lot of energy to get it to jump into that first excited state, and then it tends to then be a bit less after that. Okay, so remember, if it's emitting light, then that's when the electrons are dropping down the energy levels. Now, one thing that you are sometimes asked to do is to say how many different possibilities there are. And you would do it by drawing a diagram like this one here. So you can see, if we take, starting on the left and working across, looking at each arrow, E3, your options here for the energy levels as the electrons drop down are to go from E3 to E2, E3 to E1, E3 to E0, or it could go from E2 to E1, E2 to E0, or E1 to E0. So there are 6, if you've got 4 energy states, 4 energy levels, you've got 6 different possibilities for how the electron can jump or transition down through the energy levels. And it talks about that on the right-hand side underneath the spectrum diagram. So there are 6 possible downward electron jumps as shown by the 6 downward arrows. If you're drawing that, make sure you're drawing them downwards if it's emission. So each happens without outside influence, they are spontaneous. Now what that means is that for that particular element, there will be, and that one, the example there, they're showing it, well, it's got sodium there, but I don't think that's not necessarily meant to be sodium in the diagram. But that one there with its 6 lines, so that means that on the emission spectra of that element, there would be 6 lines on there. Okay, some of them will be brighter than others depending on how much energy there is. So if there's lots of electrons, either from that atom or from another one of the same element, then your line is going to be brighter. Okay. There's an example given there at the bottom, which is basically just similar to what we have just done. So you've got the chain working out from something going from E2 to E1. So they've worked out the difference in amount of energy, stuck that into the E equals HF. That's given the frequency, and you can then use V equals F lambda to work out the wavelength. Okay. Next page in your notes is the same, but absorption lines. This is exactly the same, but the electrons are going in the other direction because it's about then it being basically jumping up between the levels rather than dropping down. So it'll jump up between the levels if the atom is absorbing a photon that's come from somewhere else. So if the atom is absorbing a photon of energy, then that's exactly the same difference in energy between 2 of the energy levels in that atom. An electron will jump up between the 2 energy levels because it's gained that energy rather than it losing the energy. So as it jumps up, it gains the energy. How much energy it gains will then depend on the energy levels it's moving between, and then the frequency of the light that is then absorbed then is worked out in the same way. It's just that this time, so if you see this time in your diagram, the arrows are all drawn up the way rather than down the way. So there's 3 possible, in this example, 3 possible upward electron transitions. That then means that on an absorption spectra, you'd have all your bright colours with 3 black lines there where the light is being absorbed. So there isn't there's no light being emitted at those frequencies because the photons have been absorbed instead of being emitted. Example given the same, you'll see it's exactly the same as the previous one. And remember, you can forget about the negative in the calculation because it's just the difference between the 2. Okay. So that's everything in your notes. What you should now be able to move on to is questions 1 to 6 on pages 32 and 33 of your booklet, which you will see is the very last bit. I think there's a couple of questions on page 34 as well, actually. Yes, there is, so you could always do those as well. So what I've done, I would suggest that you do all questions 1 to 6. So Question 2, I've just done as an example, because that's what I was just talking about a minute ago, about where you get asked to say how many different options there are, how many possible transitions there are. Okay, so that's question 2 there. So if you find that in your notes booklet, and then you can give it a go, or just now, or pause it and come back to it, or whatever. But there you go. So the first bit is just asking how many downward transitions there are, how many downward transitions are possible between the energy levels of each atom. It's not overly clear, but that's showing 2 different atoms, atom X and atom Y, that are shown next to each other. And if you notice, the size of the gap between the different levels isn't the same every time, whereas when I've sketched it, I've not drawn it very accurately. So the first bit's just asking how many different possibilities are there. So you've got from 2 to 1, from 2 to 0, and from 1 to 0. So that's 3 different options. And then with atom Y, it's got 3 energy levels, which gives you more options. It comes out at 6 altogether. How many lines would that then mean appear on the emission spectrum of each element? So it's the same as the number of possibilities for the energy jumps, or the electron jumps. So it'd be 3 lines for X and 6 lines for Y. Part 3 of that question then asks you to copy the diagram and to show the possible transitions. So that's just that next bit there. It doesn't really matter what order you do it in, but try and do it logically, although I haven't done it particularly logically with X. But with Y, I've basically started at the top, and I've gone down 1 step, down 2 steps, down to the bottom, and then I've started at level 2 and worked my way down, and then started at level 1 and worked my way down. You could, in theory, have ones with more than 4 levels, which obviously gives you a lot more options, but I don't think they'd give you more than maybe up from ground state up to the excited level 4, because otherwise it starts getting a bit silly. Part B says which transition in each of these diagrams gives rise to the emitted radiation of, so first of all, the lowest frequency and then the shortest wavelength. So the lowest frequency is going to be the one with the smallest wavelength, the smallest energy. So that's going to be the smallest gap, which isn't as clear on my diagram. But the smallest gap in X is between 2 and 1, and the smallest gap in Y is between 3 and 2. So the smallest gap is the smallest amount of energy required, or the smallest amount of energy that would be emitted when it drops down, which would then give you, if you did put that into E equals HF, that would give you the smallest frequency. The shortest wavelength is going to be the other way around then. So the shortest wavelength is the highest frequency, so that's the biggest gap. So that's basically when it jumps from the very top right down to the very bottom. Hopefully that makes sense. The rest of your questions are there. So you need to go, basically do the same again for question 3, so how many lines can appear, and then you're starting to look at calculating frequencies. So the largest energy transition, the smallest energy transition, so that's your biggest gap, your smallest gap. And you're basically working out the energy difference at each point, and then, so it'll be, so for the largest energy transition, it's going to be E3 down to E0, so you work out the difference between the two in terms of energy, stick that into E equals HF, and that's all you have to do because it's just calculating frequency. Smallest energy transition, so it's just the smallest gap. Show whether any of them correspond to frequencies within the visible spectrum. So if you look, visible spectrum, if you go back to page 10 in your notes, where you've got your approximate wavelengths of blue, green and red light. So you're going anywhere between about 490 and 700 nanometers is visible. Okay, maybe even 400 up to 700 is visible. Okay, so you have to work out whether any of them, nanometers that is, so you'll obviously have to work out what that is as a frequency, and then work out whether any of that falls within the range. Explain whether transition would produce, which transition would produce the photons most likely to cause photo emission in a metal. that's going to be one, that's going back to photoelectric effect. So that's going to be the one that's got the biggest energy, because that's going to be most likely to be able to get over the work function. And then that's basically just more of the same for working out the rest of those questions, so that should be fine. Hopefully that all makes sense, and you have, yeah, and you're going to be able to work out those questions. What I'll then do is I will put up some other questions for you to do, some that are exam questions, and get you to work through those. And then, yeah, hopefully that's fine. And then that'll be us done. Then, in terms of the waves and particles topic, but we'll do a little bit just at the start of next week, going back over the refractive index stuff before we move on to the electricity topic. But hopefully that is fine.